Welcome to this explainer. Today, we're doing something really cool. We're pulling back the curtain on the absolute magic of cartography to decode exactly how we represent the fourth dimension, which is time, on a flat 2D screen. We're going to see exactly how data scientists take just overwhelming amounts of shifting geographic data and turn it into visuals that our brains can actually process. It's a fascinating challenge. All right, here is our system initialization protocol for today. We're going to start by mapping the fourth dimension, then map our data through the triad model matrix, decode bitemporal data, escalate into mastering multitemporal data, and finally, we'll look at how to optimize for human cognitive limits by overcoming change blindness. Let's get right into it. Section 1. Mapping the fourth dimension. When we're tracking geospatial data, we are almost never looking at just static, frozen information. Whether we're tracking the spread of a virus or massive urban sprawl, we are attempting to visualize a highly dynamic world where the geometries and the themes are just constantly shifting over time. So, the core challenge for any cartographer is integrating the when seamlessly into the where and the what. To process this effectively, the system, or the cartographer, really has to make a choice. They can choose to monitor a static spatial segment, which is kind of like observing population changes in a single defined city block over several decades. Or they can track a variable space segment. That would be like following the constantly shifting boundaries of a moving storm front as it rips across a continent. Moving on to Section 2, the triad model matrix. Now, to avoid total system chaos with all these variables, cartographers utilize this really powerful navigational algorithm known as Phukett's triad model. It's a conceptual framework that breaks every single piece of spatio-temporal data down into three core components: where it is, what it is, and when it happened. This brilliantly takes abstract, messy data and turns it into highly logical inputs and outputs. Think of this glowing matrix here almost like a terminal query or a magic decoder ring. It's actually brilliant. By inputting two known variables, let's say a specific location and a specific time, the system flawlessly computes and outputs the third. So if you know the where and the when, the system reveals the what. For instance, what exactly the population was in a specific county in the year 2010. Structuring our data this way lets us answer incredibly complex questions about our world with real precision. Next up, Section 3, decoding bitemporal data. Okay, so let's analyze how we visualize a simple A to B change. When dealing with exactly two timestamps, say 1960 and 1990, mapmakers typically extract the difference between them, and they have to choose to display either an absolute metric change, like the actual raw number of people who moved into an area, or a relative change, like the percentage shift in population density. And that choice absolutely changes how you, the viewer, perceive the trend. But here's the catch. When the location itself is actually changing between point A and point B, standard static maps just completely fail us. So we initialize what we call flow maps. These are specialized visualizations specifically designed to track both the physical movement and the quantity of objects going between geographical locations over time. Now, what's really interesting about this is how it functions almost like a live tracking system. The origins and destinations are obvious, sure, but look at the thickness of those curved lines. They are precisely calculating and visualizing the exact quantity of daily commuter flows between these districts. You instantly know where the heaviest traffic burdens are, literally without having to read a single spreadsheet. Now, what if things aren't physically moving, but they're simply changing right there in place? If you look at the sequence map on the left, you have to look at 1980, then jump over to 2000 and mentally calculate what grew and what shrank. Honestly, that's a huge cognitive load. Instead, an optimized interface uses an explicit difference map, like the one we see on the right. It instantly highlights data gains and losses. It just does the math for the viewer, making the change violently explicit. All right, Section 4, mastering multitemporal data. As we ramp up system complexity to analyze way more than just 2 points in time, we enter the really dense realm of multitemporal data. Amazingly, even back in 1869, Charles Minard created this wildly complex, multitemporal flow map of Napoleon's Russian campaign. Spoiler alert here, things did not go well for Napoleon. This plots a highly segmented path where the width of the line denotes the troop quantity shrinking across successive geographic and temporal checkpoints. It's basically a masterclass in encoding multiple variables onto a single graphic. But today, to fully immerse the viewer, we can elevate this kind of data into a full three-dimensional framework. We call this the space-time cube. What we do is project standard geography on the flat x and y axes, but we stack time directly vertically on the z-axis. This brilliantly illustrates the whole concept. You can trace the exact trajectory and speed of two distinct routes simultaneously. Because time is rising vertically here, the angle of the line tells you everything you need to know about speed. A gentle slope means fast movement. But if you see a perfectly vertical 90-degree slope, that indicates a complete temporal standstill. The object is totally stopped in space, but time just keeps moving upward. However, we have to talk about the limits of this 3D rendering. It's incredible for tracking a few specific routes, sure, but the moment you start filling this cube with complex area data, like shifting population zones, it causes immediate visual collisions. The data overlaps, creating severe visual occlusion, and it completely crashes the user's ability to actually read the information. So, to bypass that rendering flaw, the interface can deploy a technique we call small multiples. Think of it as a dense 2D dashboard array. It lines up chronological snapshots side by side. Take this incidence map of Germany, for example. By laying it out this way, the human eye can rapidly scan for pattern shifts and color intensity over months without anything overlapping or hiding. Finally, Section 5, Overcoming Change Blindness.
We have to address the ultimate bottleneck in all of this data flow, the processing limits of the human brain itself. Imagine staring at a flickering screen showing hundreds of rapid data changes on an animated map. Without highly optimized visual cues, your brain just experiences cognitive overload. It triggers change blindness, kind of like that famous psychological experiment where people completely fail to notice a person in a gorilla suit walking through the frame. You literally just failed to spot massive, critical anomalies.
So, to prevent this, cartographers have to run through a very strict design protocol. It's essentially an optimization checklist. You have to ensure extreme simplicity, minimize eye movement by keeping map images as small as possible, and ruthlessly discard any unimportant background details. You're stripping away the noise to make every single data shift violently explicit. And that leaves us with a really fascinating query to ponder. We've seen how to map time, from basic A to B differences to these massive multi-temporal arrays. But as our geographic data scales literally into infinity, with real-time sensors constantly pinging all over the globe, when does human perception tap out? At what point does the visual complexity become so great that the machine simply has to step in and do the interpreting for us? Definitely something to think about the next time you're staring at a live tracking map. Thanks for joining me on this explainer. I'll see you next time.